Hey guys, this is GKCS. We are talking about Monte Carlo Tree Search today, and this is a really interesting topic because unlike everything that we have learned in earlier in artificial intelligence, this actually uses probabilistic methods. So stuff like alpha, beta, all the optimizations we learned, Minimax algorithm, that has a concrete way to find things out. Monte Carlo seems a lot more fuzzy in the sense that it does things based on probabilities. So it's difficult to tell what the outcome will be, and in fact, if you run it multiple times with the same position, game position, the output might be different. So all of you who are interested in AI should probably watch this video. In case you're only interested in comparative programming in terms of algorithms, then this is an AI video. So this will be fun, but you might not like it. So let's get to Monte Carlo Tree Search. So the logic behind Monte Carlo Tree Search can be understood using something called trust networks. So this is something which is fun in neuroscience. Trust is something that humans do to each other. Trust networks are a network where a person trusts another individual, and you can note that down. You can take that edge of trust. Let's say you're over here. This is you, and there are different people A, B, C, and D. So trust value for A is 10, trust value for B is 200, trust value for C is 5, and trust value for D is 50. So when I say trust value, you trust them with a particular thing. You trust them with a particular job. In our game, these are moves, and the trust value is actually the likelihood of you winning after playing that move. So that's what Monte Carlo is giving us. It's giving us certain edges with their trust values. Now, logically, as a person, if this node is more likely for you to give your win, you're more likely to put more effort into this node than this one, because this is not so nice. Whenever you're played here, it seems to be losing. As human beings also, we tend to put more effort in places which give us more outcomes, in better outcomes. And so what we are going to be doing is, in the computer world, we are going to put in more computation power in this node than in this node, because this is bad and this is good, seems like. So, sorry, what will happen likely now is this node will be expanded further to P, Q, and R, and assuming that R gives you the maximum trust in this scenario, R is likely to be expanded further to D or S, T, U. Yeah, we don't really care, but yeah. So you're seeing that this tree is unevenly expanded. This is not a balanced tree by any chance. Also, interestingly, based on the amount of trust you're getting, based on the output, you are actually expanding the tree. So there's logic behind your expansion technique. Now, when we are actually expanding, we don't want to completely ignore C forever, because that is not nice. That the problem with completely ignoring C is that you might miss out some good nodes over here. So let's say till now, whenever you've gone to C, the only two nodes you have explored are these two, and they are both losses. That's the reason why you don't trust C. But the thing is, if you look at this node, it's good for you. Unfortunately, you haven't explored C enough to be looking deeper into this node. So then what will happen is, you will miss on a good opportunity, maybe even better than B, just because you do not trust this C enough. And that happens in real life also. Maybe a person, we have a bad image about that person and it turns out bad. So what you want to do is take two parameters into consideration. One is exploration, which is where C benefits, and the second is exploitation, which is where B. So exploitation is where B comes in. You have a lot of trust in B, you have invested a lot of your time and effort in B, and it's given you good outcomes till now. So you want to put even more effort in B. You don't want to be trying new things against a person who has gained your trust. Okay, so that is exploitation. Playing out B more, understanding B better, so that is the most likely move that you're going to play in the end anyway. So you should expand this further. That's exploitation. Okay. Exploration is not writing of C as a bad node, not writing this node off or this node off as useless, because they might have good opportunities down there. So you need to give them chances from time to time. So if there is, let's say, 1,000 computations that you can do, or 1,000 moves that you can play, in fact, not even 1,000 moves, 1,000 games that you can simulate. In those 1,000 games, mostly you'll play about 500 games with B, because that's a node that you trust. But you'll also give 10 or 15 games to C, because you don't want to write it off completely. What you want to do is you want to explore it a bit. If it keeps on giving you negative values for every time that you play on it, your trust reduces further and further and further, and you play it lesser and lesser. Okay. But if it starts giving you good values, your trust for that node suddenly increases, and things start to even out. So maybe it becomes 10 once it gives you this win. Right? Trust link slightly strengthened. So that's the general approach for Monte Carlo Tree Search. Let's get to the specifics now. So this is the game tree that we have drawn. It's a pretty substantial tree. For simplicity, what I've kept is these leaf nodes are either a win or a loss for red or blue. Okay, and red plays the first move, blue plays the next move, and so on and so forth. So in alpha beta, of course, you wouldn't have these kind of values. You would have heuristic values for every position. But in this case, we have something like 5 by 7, 3 by 4, because these are probabilities of red or blue winning. Every probability here is red winning, so that things are simpler. But in the code, you can always inverse those probabilities. It's no big deal. Okay, so taking an example, 5 by 7 and 3 by 4. So what that says is, out of the 7 games played, 5 of them were won by red. Out of the 4 games played, 3 of them were won by red. So its parent is going to say that from me, 7 plus 4 games were played, which is 11. And out of that, 5 plus 3 games were won by red, which is 8. So 8 by 11 is the probability of red winning at this position. Okay, that's how this entire tree has been constructed. Of course, you'll see some places where there's only blues, but I kept it 1 by 9 to just for the sake of the tree looking a little more elegant. And not just that, maybe this is winning for blue in every position, but the simulation that we had gave a red win. Okay, that is also possible. So let's get to that. The first step in Monte Carlo is actually selection. Right? When you're at your root, you want to select a node to have a look at. So if you're at your root with a 42 by 83 percentage of winning, 42 by 83 probability of winning, which node do you choose? Looking at these nodes, it seems that this is an unlikely node for you to choose. This is okay. This seems quite likely. And that's why you'll see that I have kept the probability such that 46 of the games had explored this particular node because it has a higher chance of winning. Okay, so as red, you're more likely to come here. That's the exploitation part of the policy. But you'll also play 1 or 2 games here. That's the exploration part. The selection procedure is pretty complicated, so just bear with the formula. But we already know the things that you need to take into consideration. So the first thing is to take into consideration, of course, is the value that you have there. So in our case, let's say we are trying to find the value of this node. Okay, so that is obvious. That is 30 by 46. Okay, this is the value that it gives you. Plus square root of some constant C1 into log of the number of times that you have actually been at your current position, which is from this node. So that is 83. Upon number of times that you have played this move, which is 46. So in fact, I shouldn't say that in the formula itself. So that will be the number of times I have been in my current node. So that is, let's say, n upon n of I plus this part. Let's get to it in some time. First, let's just evaluate this into C1. Let's say that is 100. So this is 100 into log of 83 upon 46 square root of the whole thing. Now, whatever you're adding here is not necessary, but it helps. It is domain-specific knowledge. For a game, there are some experts, and the probability of those experts playing this move is taken into consideration. Okay, so the other factor you could have is C2 into P of I upon N of I plus 1. Okay, this is a factor which helps you take prior domain-based knowledge into consideration. So maybe there are great chess players who will tell you that from this position I am more likely to play this position, or they might just say that I'm more likely to play this position. So you have to take that in consideration. That is specific specialist knowledge. So that comes out to be, in our case, let's say C2 is also 100. So 100 into, let's say the probability of playing this move is 5 by 8. You can take anything random. Okay, now you see that what's happening. This is Ni plus 1, which is 47. So in this case, what's happening is all of this is pre-computed. Okay, and this part is the only part that is going to define how much of a weight this term is going to have. So I'll call this domain specific knowledge, or you can call it expert knowledge. Right? This is actually the crux of the whole algorithm, and in fact this too. So this is the value of a node, and this bit, if you have a look at it, domain specific knowledge gets less and less useful as you play more and more moves in that place. Okay, so some expert tells you that I would play this move, but the more moves you explore about it, the less you care about what that expert says. This is because you are becoming more of an expert. Alright, that's the logic. That's why you have put in Ni plus 1 in the denominator. More moves that you play, the less this value is. Similarly, the more moves that you have played in this position, the less value that this term has. And the second thing is that the more moves you have played in your current position, the more value that this term has. What could this be? This is the exploitation bit. Okay, it contains both exploration and exploitation. More moves that you have played up to this point, that is exploitation, and lesser moves that you are going to play in the next position, that is exploration. Okay, so both of them are contained in just one term. Alright, if 46 was greater, then you would explore this move lesser because you already explored it enough, and if 83 was greater, you would exploit this more because 83 is large and you should respect that. Okay, fine. So this entire term of selection criteria is taken care of. What you're going to do is you're going to run through all i's for all I. You're going to find the max of this term and simply pick that up for selection. Right, so whichever term gives you the maximum from here is picked up for selection for the next round. So just to clarify things mathematically, this node is more likely to be played because it has a higher value. But eventually what's going to happen is that you'll come to a position where, let's say, you play the same move 200 times consecutively. Alright, so instead of 46, this becomes 246. Alright, and your domain specific knowledge becomes redundant because this denominator is pretty high. Upon log of, instead of 83, it's going to become 283 into some constant factor, root of this plus v of I. Now, log of 283 upon 246. You see that log of anything increases very slowly, while this term increases very fast. So this overall term is going to be small for this node. But on the other hand, let's take 1 by 8. The number of times you have played this is still 8 because you haven't increased the number of times you only put all your effort here. So this is going to be 8 upon log of 243 into the same constant factor. Now you see that this term is pretty big now. Plus whatever the value 1 by 8, and this was let's say is 246, you want 200 moves. Suddenly you see that at one given point of time, the term here is going to be so large that it's going to overtake the sum here. So this sum is going to overtake this sum, and you will then play a move here. Okay. Before we play a move here, of course, you'll be ending up playing a move here. So that's the logic of Monte Carlo Tree Search. If you are investing too much time here, you should explore a little more, but you should spend more time there, and that's why you have the denominator below. The second step to Monte Carlo Tree Search is actually very easy. It's just called simulation or a play out, in which case all you need to do is just play random moves at a given position till you have a result. If it is a positive result, then yeah, that's taken into consideration. If it's a negative result, of course, you take that also into consideration. So simulation is just playing the whole game out and seeing whether you win or lose. Now, when does the simulation actually happen? When you come to a node which you have not expanded yet, you play the whole game from this place randomly. Okay, so in chess, maybe you have 15 moves that you can play, and you just choose one in random, and from that position, you choose another random move, and so on and so forth. Okay, that's what Monte Carlo simulation means, random. Except, you could use pseudo-random moves also. You could use a very simple heuristic, which takes very little computation time. Okay, in chess, don't get checkmated is one pseudo-random heuristic. Another is the maximum material that you can gain. So pseudo-random is a cheap heuristic which helps you make almost random moves, not the best moves obviously, almost random moves, and tell you what the evaluation of that position is. Okay, so that's what simulation is. From a place that you cannot expand further, you completely play a random game. You note that whether that's a win or a loss. Okay, the third part is very closely tied to simulation, which is backpropagation. Backpropagation says that when there's a win or a loss, you need to propagate that result upwards. So from here, taking an example, if red wins here and you had played a move here, so this becomes 8 times that you have played here, and red won. So 6 out of 8 times is when red has won. Going up, you have 9 by 12 as the new probability of you winning here. Okay, and similarly, this becomes 30. So 12 by 30 is your new probability. Don't try to round this off, because if you round it off, you won't be able to get the proper probability next time. And this becomes, of course, 84 is the number of times you have played here. 43 by 84. So that's more than 50%. Okay, so you're seeing that you can go to a particular position, simulate the entire game. Once you have simulated it, you can then backpropagate that result. Okay, the final step, which is actually most probably considered the third step, is expansion. What happens is, once you come to this node and it reaches a particular threshold value, maybe you have come to this node 100 times, and now you decide that no, this node is not worth exploring every time, is not worth simulating every time. What I need is more concrete information about this node. Then you get rid of the result from this node. You get rid of making simulations every time, and you actually expand this node to all the moves that you can play from it. Now, these nodes are places where you'll be doing simulations and backpropagations from. Let's say these 3 are wins for red. A lot of drawings going on here. So these 3 are wins for red, and the probability of you winning here is let's say 3 by 4. So then expansion has also turned out to be quite easy. You just come to a node, you check if the node has not been expanded, and if it is exceeded a threshold value, then you expand it to the number of possible moves you can play. In each state, you are going to do some simulations, let's say 10 simulations for every move. Note down the probabilities of winning, push that to the parent, this is the backpropagation step, and then you push that forward till the root. Okay, so every expansion requires a simulation, every simulation requires backpropagation, and the first step was selection, which is the procedure through which you actually come to a particular node. And this is interesting, because once you're done with this, once you're done with the entire tree, all you need to do is go to the root, find the most likely winning node, and just return that. Okay, so pretty interesting Monte Carlo Tree Search, but there is one nuance. So let's try to find out how it performs against alpha beta. So to really contrast alpha beta from Monte Carlo, what we're going to do is we're going to use this example. Okay, and let's first try to solve the example using alpha beta. So you see here that blue and red are playing against each other. Each move, they are alternating in between moves. So this is being played by red, this is being played by blue, and so on and so forth per layer. These are heuristic values, which can be considered as gray areas. You're not sure who's going to win. They're just indications of who's winning. Okay, negative for blue, positive for red. All right, now we can solve it. This node colored blue means that blue has won, and the node colored red means red has won. So according to the Minimax algorithm, red will be choosing this node because it's the maximum amongst all the other possibilities. So this node becomes red. Okay, pretty simple. So red is winning here. Is there any chance that blue is going to choose it? No. Blue will never choose this node because it's going to lose. So blue is trying to minimize its score amongst the 3 scores it can get, and it's going to be choosing -1. So this node evaluates to -1. You come to the root, you come down here, again, standard alpha beta, -5 will be chosen because you're trying to minimize, and then -2 will be chosen once you come back here, because blue is always trying to minimize. This is min-max. Right? Red says, I want to maximize my possibilities amongst these 3, and it comes and chooses -1, which is actually the maximum amongst the 3 possibilities. So, something fishy going on here when it comes to Monte Carlo. Monte Carlo is going to be using something probabilistic, remember. So, if you have a look at these 4 nodes, what is the probability of red winning when it's at this node? 1/4. Of course, I'm sure most of you calculated it. I don't know why I said it with so much authority, but 1/4 is the probability that you're going to be winning as red in this state. So 1/4 is a pretty poor probability of winning, and at this point what will happen is red will not like this node. It's going to report more losses compared to the number of wins it's having. Now let's get to the parent, blue. If there are more losses for this node as red, that means there are more wins for this node as blue. So blue is going to say, I would like to play this move. Very weird. When you think about alpha beta, blue wants to play a move which is forcefully losing. And similarly, because blue is reporting that I'm more likely to win in this move, red, its parent, is not going to be playing this move. Okay, because the reports are such that you are more likely to win as blue if you play this move, which means you are more likely to lose as red if you play this move. Okay, so red is probably going to be coming here, where it has a 1/2 probability of winning. And even here it has about a 1/2 probability of winning. Here, its probability of winning is, let's say this is a win, this is a loss, and this is another a loss for red because it's being reported as such. In that case, what's happening is its probability of winning is reported as 1/3 for this scenario, 1/2 for this scenario, and 1/2 for this scenario. Okay, so this is a very interesting algorithm, and that's what I'd like to conclude with. Actually, versus alpha beta, I'm not sure which is better, but it depends on the game and depends on the situations that you're facing more often than not. If you like the code for this, I'll just put it in the description below. I haven't still written it. There's some very interesting links on Monte Carlo simulations and Monte Carlo Tree Search. I'll just put them in the descriptions below. The next topic is going to be decided by you guys because I'll just put a straw poll and let's see where we get to. So until next time then, see you.